Subscribe to Tech Talks and hit the bell icon to get notifications about coolest and latest engineering technology in the first place.
In this session, we will see the difference between Sine PWM and SVPWM. So for that, what we will do, we will take an induction motor and we will feed this induction motor through a VSI voltage source inverter. We will keep the voltage of this VSI inverter same. We will keep the motor's parameters same, and then we will study one time we will feed this motor through a Sine PWM wave, another time we will feed this motor with an SVPWM wave. So as you could know that in my previous videos I have shown you the Sine PWM in V by F mode and SVPWM. You could refer over here, so you could refer this my video. The link is already coming on the screen for SVPWM, how it can be implemented, and you can also refer to the Sine PWM that in V by F. So a part of this one we will be studying over in this session. So this is my SPWM, as you could know from my earlier video. So this is the control circuit of V by F. Okay, from here it is the generated sine wave. Okay, and these are the switching pulse of switch 1 to 6. It is going to the inverter. I have kept the inverter voltage as 700 volt. Okay, let's see that inverter voltage is 700 volt. Okay, and next the inverter is connected to the motor, and some outputs are there, that is rotor speed and torque, stator current, all those are taken out. Okay, and also what I have done, I have made a reconstruction of the phase voltages by using the switching table. Okay, so this can be easily implemented by this one. So the VAN, the average voltage of A phase, is VDC by 3. This is the DC voltage. Okay, VDC by 3. 2, this is the switching switching of the switches. This refers to switch 1, this is switch 3, and this one is switch 5. So VDC by 3 into 2 into switch 1 minus switch B minus switch C, and accordingly it will give for the B phase and C phase. Okay, so this equation I have implemented over here, as you could see. This is my VDC by 3, that is 700 volt DC by 3, and this one is say 0. So it is the implementation of this equation. Okay, so what it will give me, it will give me the reconstruction of the phase voltage. So I will now connect this one to switch 1, this one to switch 3, and this one to switch 5. Okay, as it is given over here, that is switch 1, switch 3 and switch 5. So it will give me phase voltage of A, phase voltage of B, phase voltage of C. But I don't require all these phase voltage, I just require one phase voltage, that is this one, phase voltage of 1. I put it into for a second one. I require the phase voltage of the line current, phase. Here the since it is star connection, so line current and phase current are same. I require the same phase current. Okay, and the one, this one, I will give it to the generated sine wave, that from where it is compared with the carrier wave, that is the triangular carrier wave. The triangular carrier wave what I have kept is 5 kilohertz. Do remember that the carrier wave is 5 kilohertz. You can refer to my earlier video. You will easily find out that the carrier wave will be 5 kilohertz. Now what we will do, we will just compile this one and see what happens. Okay. Oh, okay. One thing we have to do, we have to go here and you just do this one. You go to configuration properties. You go to configuration properties and you go to login. In login you select this one, that log data to workspace. You give any name over here. As I am given voltage current and SPWM, and you just select dataset. Okay, and then you just compile it and run it for some time, so that the motor is at steady state and your reference sine wave is at 50 hertz. Okay, my motor is of 50 hertz. You could see the motor parameter. Okay, so it is a 50 hertz motor. You see 50. So I will wait till the motor reaches 50 hertz. Let me check if it has reached 50 hertz or not. I will wait for some more time till it becomes 1. Okay, it has reached the required speed. So I will just stop it now. So we will go to here and we will go to tools and FFT analysis. Okay, and here we will put this one, that voltage current is PWM, right, FFT window, right, and other things are okay. We will put it as harmonic order. Okay, and we will place here display. Okay, so this is what this will do. This will just produce the FFT of the signals that we have logged in. Okay, now we will analyze this one. We will go to axis properties. Right here we will go to axis properties, and in y axis over here we will put 110. Okay, so here in this figure you could see that the fundamental, that is a 50 hertz one, this one is having the maximum magnitude, whereas the other parts are not having any component. There is no harmonic present. So that is what is expected, because in Sine PWM we were just comparing the sine wave with the triangle wave. So sine wave will be having only 50 hertz and only fundamental will be present, and no other harmonic part will be present. So harmonic part will be present where? It will be present in voltage and current. Okay, so let us see that what is present in voltage waveform and in current waveform in one cycle. So again we will do this FFT. Okay, but this time we will change this one to input 2. Input 2 is what? Input 2 is the voltage. So this is the voltage of one cycle, right? So now we will put display. Okay, and we will just place it so that we can study well. This is, and here we will be putting as 105 only to get a clear view. Okay, you see the voltage, the TSD is 79.45%, right? in voltage the TSD is 79.45 for SPWM. So as you could see from this upper waveform, there are a lot of harmonics are there. Okay, so it is 79.45. Now let us see that which harmonics are prominent. So I will just put here 5. Okay, so that the other, so you could see, I will just put something more. I will just put 1 over here. Okay, so the maximum value is 1, and you could see that the third harmonic, then this 14th harmonic, these are quite prominent. Okay, these are quite prominent, but not so prominent because it is only constitutes less than 0.2% of the fundamental. Okay, but harmonics are present. Now same thing we will be doing with the current waveform also. The current waveform, where it is logged in input 2. You could see, I am showing you once again that this is the oscilloscope where we have put which one we have logged in, right? Simulation properties, you see the logging, you see that these data are logged to the workspace. Okay, and what voltage signals are over here? The signals over here are the current, third one. The second one is the voltage that we have reconstructed from the switching part, and the first one, this one is the sine that we have sine, or the reference wave from which it is taken, right? Now we will see the third one, that is the current. What is the harmonic present in the current? Okay, so we will put it to input 3. We will put an FFT window, so it is 50 Hertz. Okay, we will place a display, and we will just enlarge this one so that we could study it well. We will go to access properties. Everything is there. We will just put 105 over here. So you see the THD is what? The THD is the current harmonic is 4.62. 4.62, right? And what other harmonics are present over here, that also we will see. I will just place 2 over here. Okay, so let us place 5. Okay, so you see that the DC values, some DC values are present, and the third harmonic, second harmonic, these are present but not so prominent. Okay, it constitutes less than 1% of the less than 1% or less than 0.5% of the total waveform. Okay, and you could easily see there from this part. Okay, so we will just keep a note of this THD that is present in the waveform. So this is all about Sine PWM. Now we will repeat the same experiment. We will repeat the same experiment, and we will feed this one with space vector PWM. Okay, in this case what we have done, we have just put Sine PWM in this pulses in this IGBTs, and in the second case what we will do, we will put the SVPWM pulses in these switches, and what we will see that what happens. Okay, in this section we will see about the SVPWM. So for SVPWM, what I have done, so this is the same thing, the same switching function from where I have used the switches to formulate the voltage. So I have taken the phase voltage of one phase, the phase current of the same phase current, and this one, as I have put previously, the reference wave. So here the reference wave is not sine wave, but it looks something different. Okay, so let us see that how this reference wave looks like. So this is the internal part of SVPWM. This is already shown in my previous video. If you have not seen my previous video, just check the link in the description box. It will be easier. So please be noted that the carrier wave or the triangle wave is 5 kilohertz in both the cases. Okay, so this is the reference wave and the carrier wave. Okay, so this is the reference wave. As you could notice, I am showing you one cycle, that this is the reference wave. Okay, and this is the triangular wave or the carrier wave. It is 5 kilohertz, and this reference wave is of 50 hertz. Okay, as you could see a dip in the middle. Okay, so this is the sine space vector PWM reference wave. So what we will do, we will just take this wave out. Okay, we will put here reference. Okay, and we will put it to here. Right, so this is reference, and we will put another thing over here. I'll put here reference. So that I am doing is just for convenience, so that it will be easy for us to locate in a single oscilloscope. Okay, so this is the reference one. So I will put this one here as the previous one. So now the sequence is same: the reference wave, the voltage, phase voltage waveform, and the phase current, right? And this is the overall of SVPWM, as I have shown you earlier. Just I have taken this wave out so that it is easy to handle, right? So now we will be compiling it and running it. So it is already running. We will wait for some time, and then we will do the same process. Okay, I think it is done. Whatever is required, it is done. Now we will just see that we have logged in everything or not. Configuration, logging. Yes, we have logged in, and the name of this scope is current voltage. Datasheet set is there. Okay, so now let us go to this continuous tools, FFT. Yes, this is the current voltage input signal. You see that we will be doing the FFT of this one. So you see that since this wave unlike the previous wave, this wave is unipolar, not bipolar. If so, we will just ignore the DC value. Okay, since this wave is unipolar, we will just ignore the DC value. Other things are okay. Now we will go for displaying this wave, right? Wow, edit axis properties here. This is okay. So you see, this is the DC value. We will ignore it. It will come because the wave is unipolar. If it had been bipolar, then this value would become 0. So this one, you see that this value, only the fundamental value is prominent, and other prominent value is the third harmonic. The third harmonic is prominent over here, right? So what is the value of the third harmonic? The value of the third harmonic is 20%, that is 1/5 of the total fundamental value. So if you just look at here, that the THD is around 20.8%, and the third harmonic that is present over here is 1/5 the original value. So this is the change in the reference wave, right? Now we will see what is the change in the voltage wave as compared to Sine PWM. Now we will see what happens to the voltage value. So for that, what we will do, we will go to continuous and FFT analysis, then input 2, because our voltage is placed in input 2. FFT window, you see that only one cycle has been selected, right? So now we will place display, and we will just enlarge this one, okay, for better study, and we will put here the 105. Okay, so you just look at this, the THD, it is 54.25% THD. Okay, and other things are okay to age 54. And let us see that what other harmonics are present over here. For that, what we will do, we'll just place 1 over here, or you can place 2. Okay, so this is the harmonic that is present over here. The third harmonic, sixth harmonic, eighth harmonic, 13th harmonic. These are prominent, but not very much prominent, because it is less than 1%, less than 1% of the total, or less than, the highest I could find is less than 0.5%. It is less than 0.5%, so you could easily understand that harmonic is much less. Earlier in the voltage waveform of the Sine PWM, the THD was 79.45%, but here it has reduced to 54.25%, right? So in both the modulation index has been taken as 0.5, more than 0.85 modulation index, and taken as 0.85, right? Now we will see that what happens to the current, what is the wave harmonic that is present in current. So for that, we will again repeat the same thing. Now current is present in third one, the FFT window, one cycle is there, okay, and we will just display this one, and let us see the axis properties. It 105. Okay, so the THD present over here is what? THD present over here is 3.65%, right? So only this much of THD is present over here. So you could see that when we change the increase in THD in our reference waveform, right, that just decreases the THD in voltage and current waveform. So space vector PWM produces output that is more near to fundamental in the more near to the fundamental. We will just make a summary of these two in the next section for more but better understanding. So in this section, this is where is the summary of what we have done till now. In Sine PWM and space vector PWM, the reference for Sine PWM, the sine wave is compared with the triangle. So the fundamental, it has only fundamental, so the THD is 0%. Here the THD is 20.8% and presence of third harmonic was observable, and it is 1/5 of the value of the fundamental. The carrier was the triangle wave of 5 kilohertz frequency. The voltage was having a THD of 79.45%. However, in space vector PWM, it is 54.25%. And in the current, the THD was 4.62%, and for space PWM, it is 3.64%. So you could easily understand that in reference with the increase in THD for SVPWM, there is a decrease in THD in both voltage and current waveform. Okay, phase voltage and phase current waveform. Okay, obviously these THDs are going to change with the change in modulation index. We have kept a modulation index of 0.85 for both the cases, right? So this is all for now. If you like this video, do press like and share with your friends. Subscribe the channel if you have not subscribed this one, and comment below that more such contents that you want to hear or that you want to update. Okay, thank you for now.
Comment below about how you like this video. Check out the links in the description box about more such videos. Do click the like button if you like the video. If you are new to this channel, subscribe Tech Talks and don't forget to hit the bell icon.